Hello everyone, today I'm going to show you how to plot pseudo-acceleration and pseudo-velocity response spectrum. Just like my previous video, you can check it in the description of this video. I will plot this graph, but in this tutorial I will use the state space method. I'm not going to use the same method as previous video. It means that we have the equation of motion here, and this time to solve this equation I will use state space method, and to do that we just define a variable z that it's a vector that contains deformation and velocity. So we just do derivative of zt and we get this, and we define a equal to this matrix, and vector f contain the acceleration from ground motion. So we got this, and to solve this equation we got the result here. So the important step of this method is you have to find the eigenvalue of matrix A, this one here, and you can find AD and BD. After you can find AD and BD, you can solve this equation. I'm not going to explain too much on this method. You can check it from any textbook of dynamic and vibration. So to plot this, I will use the data of earthquake record from EL-CENTRO, and in this video I will show you how to plot this graph by using Python code. So I use the Visual Studio Code. You can use any IDE that you are familiar with. So now I'm going to create a file, a Python file. I just name it response spectrum.py. So now we need to import some library. In order to plot the graph, we need the library from Matlab and the library to do some mathematical calculation like NumPy, and we also need pandas library in order to import the data from Excel file, this one. So first I'm going to import NumPy, and sorry, let me change the font here. Let's see. Okay, so next I'm going to import Matlab, pyplot, and I'm going to import pandas. Okay, now let's import the data from EL-CENTRO Excel file. Okay, I need call this EL-CENTRO data. So I will use the command from pandas library. I name the data as EL. Okay, so I use the command read Excel. Sorry. This is the name of the Excel file here. Okay, so as the previous video I show you, the Excel file in the first column is time, and the second column is the acceleration of the earthquake. Okay, so I will define T as the time from the EL-CENTRO data. So this means I will take the first column of the data from EL-CENTRO here. Now I will take the second column. I define E as the vector of acceleration from earthquake. So I just define E that contain it's the vector that contains 0, and the length of the vector is the length of the EL-CENTRO data. So okay. And now I replace the 0 data in vector E by the acceleration, the earthquake acceleration. Okay, so we got our data here. Now we need the input data. We need the data of the system. So let's say put input data. Let's define size equal to 0.02, m equal to 1, delta t equal to t in the second row minus t in the first row. Delta t is the time interval, and now the time period bit t, I will create a vector. The length is let's say 301. So t t is equal to let's say from 0.01 to 3 seconds, and there is 300 steps. Okay, so we got our time, the range of time period bit t. So we need to define omega n, the natural frequency. it's equal to 2 pi divided by t. Now k is the stiffness, it's equal to m multiplied by omega n square. Okay, sorry. Okay, now we got our input data. So all we have to do, we just apply the method of state space here. In order to do this, I will create another Python file. It's the function of state space. Okay, so first I will put solution here, and let's call it state space dot py. Okay, we need to import some library also into this file. So I'm going to import numpy, and I need skip p also. Skip p is for inverse matrix. Okay, so first we put the command def, let's say state space, and the input data side k. Okay, let's use the matrix k omega n letter t and e. So first let's define the maximum deformation. Let's call it u0. I just create a vector, a 0 vector. The length of this vector should be the length of the vector omega n. Omega n and 1. So it's just a vector that contains 0. So to solve the equation, we need to use loop function, and we have to remember that each omega n, the number in one omega in vector omega n, we need to solve for one u0. So we need a loop that run each time of omega vector omega n. So let's say j in range of length omega n. Okay, so alright, let's look at the formula here. So first we should call for the number of omega that contain in the vector omega n. So let's call it wn. Okay, it should be from vector j 0. Now we need to define the matrix A here. Okay, let's call a function array. It should be 2 by 2, so I create here 0, 1 and minus wn square and minus 2 multiplied by psi wn. So this is the matrix A here. Now we need to define the eigenvalue of matrix A. This one is the eigenvalue and this is the eigenvector. So I will use the command from the library skippy. Okay, so let's call D as the eigenvalue and V is the eigenvector. It's equal to, this is the command from the skippy library here. So this is mean that we will take the vector matrix A here and it will return the eigenvalue and eigenvector V here. Okay, so we got D and V. Now all we need to do is we need to find AD and BT. Okay, AD equal to V here. So let's find this number first. Okay, let's just define it by EP. It should be okay. This one should be a vector. Sorry, should be a matrix. So I will define matrix here. It should be 2 by 2, and this matrix is the diagonal matrix. So this matrix is the eigenvalue here. So we need to take the data from D here. D, it will return from this command as a vector. So first I need to know D is the vector 2 by 1, so I need to call the first row of the vector first. So it should be 0 multiplied by data t here, and then 0. So this is also the same, but we will not use the first row anymore, we will use the second row, so we put number 1 here. So we got the matrix EP here. Now I'm going to find AD. So let's call AD equal to with the V. So the command dot here, it's just a command from numpy, and it's multiply matrix by matrix. So this means that the matrix V will multiply by the matrix EP here, but we need another one here. So we need to dot we need to inverse the matrix V. Okay, so now we got the matrix AD here. So next we find BD, and BD here is equal to the inverse matrix A multiplied by this parameter. So now I need to inverse the matrix A. And multiply by, sorry, this one should equal to AD here, so I will just put AD here, but we need to minus the matrix identity here. So we need to define the identity matrix. The length of this matrix is, put the matrix A here. Okay, so now we got the matrix BD. Okay, so let's look at the result here, this one. However, I need to define the initial condition. So let's say Z equal to matrix, now it's a vector 0 and 0. It's a vector 2 by 1. Now let's define the deformation and velocity. Let's say D is deformation, and let's create a vector 0. The length should be length of the EL-CENTRO data 1. Okay, now the velocity, sorry, so in order to find the solution of the equation of motion, we need to run a loop, because each data from the earthquake acceleration, we define one deformation. So in order to find the maximum deformation, we need to run through all the data from the Excel file. Okay, let's define a loop. Let's call it I in rank of the earthquake data, and okay, now let's put the result here. This one is AD and this one is BD. So we just say Z equal to okay, I will define the number from the real number from this the matrix, this matrix first, because when we define, I mean when we find the eigenvalue of the matrix A, it will turn into the complex number, but we only need the real part of the complex number. So I put the comment real here, so it will only take the real part of the complex number. Now I will multiply the matrix AD by the initial condition here, so, and plus BD and multiply by FK, and FK is this vector. So this is basically E. Okay, so let's call real BD dot. So this is the matrix 2 by 1, 0 minus I, and this is the gravitational acceleration. The unit of this number is inch per square second. Okay, so now we got our solution. Now we define the deformation and velocity. So deformation is the first row of vector z, and the velocity is the second row of vector z. So let's just say d should be di equal to 0 and vi 1 0. Okay, so that's all for our loop. Now we got the deformation and velocity, so we need to find the maximum deformation for one loop, I mean the complete loop here. So we need to find the maximum deformation. J here is the number of the loop, first loop here. Okay, let's say max, the absolute number of d here. So now all we need to do is we need to return a function here, what we want to return. So we want to return the maximum deformation here, so let's say return u0. So that's all for our function state space here. Okay, now I'm going back to the main program here. So I just call, sorry, we need to call the function first. So let's say from state space, import state space u0 state space. They put the input number I am sorry I just copy here. Okay, so that's all for our function. Now we got the deformation. Okay, so let's define the response spectrum. Let's say we use response pseudo velocity. It's equal to omega n multiplied by u0, and a is equal to omega n square multiplied by u0, but we need to divide by the gravitational acceleration. So now we got the pseudo velocity and pseudo acceleration. So all we need to do is plot the graphic. So let's say plot response spectrum. Okay, let's try plot. So this one is command from Matlab here. Let's say plot. Okay, now I'm going to try plot the deformation first. Try run it. Okay, so let's see. I think we got okay. I think it's okay. So let try add something. Okay, okay, I'm going to maximize the plot window automatically. So okay, I use this command. Okay, now let's try run it again. Okay, I think it's good. Now we put the three graphs here in the same figure, so we have to use subplot. Let's say 3 1 1, and there is the subplot of the function. Let's define the color. Okay, let's say red, and line width 2. I'm gonna put the title here. Let's call it response spectrum. Let's say font size 12, font weight is bold. Now okay, let's put the Y label. Let's call it deformation response spectrum. Okay, the inch. Let's say font size 10, font weight bold. Okay, now I'm going to limit the axis. Let's say 0 to 3, y 0 to 12. Okay, so let's try the next plot. Is for velocity, pseudo-velocity. So I'm going to delete the title here. This one I'm call it pseudo-velocity V, and it's intersect the same 0 to 50. Okay, now let's another one. This one is A, and it's pseudo-acceleration A, and it's G. Okay, now 0 to 1.5. Okay, so okay, let's put the H level here. It should be TN. Let's say font size 12. This one, okay, I'm gonna add something here. Okay, this command here will make the text inside the bracket here bold, and I should make the end here is subscript. Okay, now let's try to run it. Okay, I think the result here is great. Okay, but the text here is too long, so I'm going to put the text. Let's try put this. I should deformation, and this one also. Okay, now this one. Okay, let's try to run it again. Okay, it's a lot better here. Okay, so that's all for this tutorial, and this is look exactly like this. So the result we got here, we use Python and we use the state space method to solve for the equation of motion. So we still got the same result here. This one. Okay, thank you for today. Thank you for watching. Good luck.